Hi, my name is Noorani, and our presentation will be on nuclear power in space. Specifically, this presentation will focus on answering the research question, how will contemporary and future research affect the future of technology in space, specifically in the areas of nuclear energy and propulsion? Some questions answered in this presentation include, is nuclear energy a viable option for propulsion in space? What is the future of nuclear energy production in space? What obstacles are preventing development of nuclear power in space? Looking at the presentation as a whole, this presentation will be going over the background of nuclear power in space with Tyler Gates, current applications of nuclear power in space with Brandon Lico, future applications of nuclear power with Elijah Akins, and finally, some obstacles hindering nuclear power in space. Now we will move on to the background of nuclear power.
We'll begin with an overview of the history of nuclear technology in space. These technologies can be divided into two main groups, fission and radioisotope-based power systems. The U.S. has only a small history with fission-based power systems in space. Only the 1965 experimental SNAP-10A reactor has been used, and it only operated for 43 days due to a non-reactor-related incident. The Soviet Union launched over 30 reactors into space with varying results, from huge catastrophes to long-lasting missions. Fission reactors are more efficient and have higher power capacities compared to other energy sources, but they are more complex and therefore are more prone to failure on long missions. Much more experience has been gained with radioisotope-based power systems. The simplest form of radioisotope system is a radioisotope thermal generator. These simply use the decay heat of a radioisotope, such as plutonium-238, to keep systems at proper operating temperatures. Several of these can be used with thermocouples to create an electric generator. Thermocouples are simply two dissimilar conductors in contact with each other that produce a voltage when a temperature differential is applied. With enough of these, it is possible to create sufficient electricity to run numerous pieces of scientific equipment. RTGs have the benefit of being simple and reliable, but they can only produce a relatively small amount of power and are very inefficient. RTGs have been used on most of NASA's deep space missions, including Voyager, New Horizons, and the Mars rover missions. Voyager 1 has been operating for over 30 years on its RTG and is expected to operate at full capacity until 2020, with full failure at 2025.
We will now be covering current applications of nuclear power in space. One application is the Curiosity Mars rover. The Curiosity rover, currently operated on Mars, uses a multi-mission radioisotope thermoelectric generator. Past missions used solar panels. However, they were hindered by the dusty Mars surface. The MMRTG uses 8 RTGs stacked on top of each other to provide both heat and electricity for the Mars rover. The MMRTG on Curiosity is predicted to last for over 2 Earth years. Another application is the Jupiter Icy Moons Orbiter, or JIMO. JIMO is part of the ambitious Project Prometheus, which focuses on the development of nuclear power generation and propulsion in space. Throughout its main voyage to the Jupiter moon, JIMO will be propelled by an ion propulsion system and powered by a small fission reactor. The fission reactor on JIMO would provide 1,000 times the electrical output of conventional solar or radioisotope thermoelectric generator-based power systems.
Now we will discuss the future of nuclear power in space. One of the promising areas of future research is nuclear thermal rockets. Nuclear thermal rockets function on the principle of heating a working fluid, typically liquid hydrogen, with a thermal nuclear fission reactor burning uranium fuel. The liquid hydrogen rapidly expands in volume as it is transformed from the liquid state to the gaseous state. As this process occurs in the nozzle of the craft, a usable thrust is generated. By carefully controlling the nuclear power output of the reactor, the thrust can be varied accordingly. Nuclear thermal rockets are classified into 3 categories based on the relationship between how the nuclear reactor heats and interacts with the working fluid. In the solid core nuclear thermal rocket, as seen in the top portion of the slide, the working fluid flows through the core, much like the terrestrial-based fission reactors used for electricity generation. In the liquid core nuclear thermal rocket, as seen in the bottom portion of the slide, the uranium fuel and the working fluid are mixed together through centrifugal action. The much denser uranium is separated from the working fluid before it is allowed to expand in the nozzle. In the gas core nuclear thermal rocket, as seen on both the right and left portions of the slide, the uranium fuel exists in a gaseous state within the core. Gas core nuclear thermal rockets can be further subdivided into open cycle gas core NTRs, as seen on the left portion of the slide, and closed-cycle gas core NTRs as seen on the right portion of the slide. In open-cycle designs, the gaseous uranium fuel exists in a toroidal void created by the turbulent flow of the working fluid. In closed-cycle designs, the gaseous uranium fluid exists contained in a quartz container. Besides the different state of this fuel, the design is similar to conventional solid core designs. Another future application of nuclear power in space is electricity generation. The Stirling radioisotope generator promises to provide greater electrical power output while remaining less massive than a comparable power output RTG. The Stirling engine is an externally heated, closed working fluid system. Nuclear decay provides the temperature differential that the Stirling engine requires to operate. The Stirling engine then powers a high-efficiency generator to produce power. The Stirling radioisotope generator has been extensively tested, however it has not been flight tested in space.
Now we will be going over some of the major obstacles to nuclear power in space. One major obstacle is funding. The simple fact is that the field of nuclear power in space does not have enough monetary funding to allow for these projects to be sustained and for research to continue. For example, Project Prometheus's budget decreased from $430 million in 2005 to only $100 million in 2006. Also, as you can see from the chart, NASA's budget has been reduced significantly over the last few decades. Another major obstacle is the long development time. These projects take a long time to complete, which dissuades people from investing in these projects because there is no final product for years due to the long development time. Finally, another major obstacle is the availability of radioisotopes. In the past, the majority of these radioisotopes used in the projects were produced and sold by Russia. Unfortunately, they are no longer able to provide these radioisotopes, thus preventing these projects and research from progressing. Hopefully, if we're able to overcome these obstacles, the implications of nuclear power will be immense. One implication of nuclear power in space is in the field of science and exploration, in which the world would be offered a better understanding of our universe in general. Nuclear power in space also would have major technological implications because the technology used in space, such as small fission reactors and propulsion engines, could be applied to the technology used in our daily lives. Finally, in conclusion, we would like to say that nuclear energy in space is definitely a possibility, but it won't be possible if the proper funding, time, and resources are not available. Also, the future of nuclear power and propulsion in space currently exists within the Stirling radioisotope generator and nuclear thermal rockets, and that currently the application of nuclear engineering in space is through the RTG rather than fission reactors because of efficiency. Finally, here are some more resources and references on these projects.